Algebra 2, 5-7, apply the fundamental theorem of algebra. So first is the idea of a repeated solution. A repeated solution is a solution that appears more than once. I have no idea how the color just changed. So an example of this is if I had a quadratic that I was solving that was 0 equals the quantity x minus 1 squared. We know that if I was going to write that as two factors, it would be an x minus 1 times an x minus 1. And if I solved both of those, and usually we don't, right? Usually we do the square root, we just get one answer. But if I was to write it out and solve both of them, they would both equal 1. So in this case, I would say that x equals 1 is a repeated solution. Another way that we'll word it sometimes in math books is that there's a multiplicity. So I might say that the answer is 1 with a multiplicity of 2. So that means the answer is 1, but it happens twice. So first is that idea of a repeated solution. So the fundamental theorem of algebra sounds like it's going to be some kind of big, amazing thing, but it's something that you probably had already kind of figured out for yourself. It's also it's almost anticlimactic. So if f of x is a polynomial, I feel like this is the big reveal right now, of degree n, where n is greater than 0, then the equation f of x equals 0 has exactly n solutions. So let's think about what that means. That means if it is a quadratic, that's an x squared, there are exactly 2 solutions. If it's a linear equation, like 3x minus 7 equals 5, there's only one solution because x is to the first power. So I think you kind of already saw that pattern with linear and quadratic equations, and maybe you noticed it with the higher degree equations that we're solving right now, and maybe you didn't. But that is our fundamental theorem of algebra. So for example 1, we want to know how many solutions is the equation x to the 4th plus 8x squared minus 5x plus 2. So highest power here is a 4, so this is degree 4. So there are 4 solutions. And the next one, how many zeros is a function f of x equals x cubed plus x squared minus 3x minus 3? Degree is 3. So there are 3 solutions. It doesn't mean that some of them aren't imaginary or they're repeated, but there are 3 solutions. So keep that in mind. Sometimes when we solve, we throw away those imaginary solutions. And the 3 could include imaginary solutions. So let's remember that we can use synthetic division if we need to determine zeros. Remember, we use the P over Q and as guesses, and then we go through and work them out if we have to. Woo, sorry about that. So don't forget about that. And for example 2, we're finding all the zeros, and there's a quadratic here. So one thing that I could do, I could list my P's and Q's as guesses, and I could go through and solve. But I'm also noticing I have 1, 2, 3, 4 terms only. That could be factored by grouping also. And I'm noticing that I have a 1x to the 5th, and then a minus 4, and I have a 1x squared and a minus 4. So there's a really good chance, because of that repeated pattern, that I might be able to factor by grouping instead. So don't forget about that. There was a problem on our notes the other day that we could have done factor by grouping on, and I don't think anyone picked up on it. So always watch for that. So this means I'm going to put a 0 in here. I'm factoring by grouping from my first 2. I can factor out an x cubed. And then I'm left with x squared minus 4. And from the second 2, if I factor out just a 1, I would have x squared minus 4. And so now I can factor x cubed plus 1 times x squared minus 4. And then I can keep factoring. This is the sum of cubes. So the first binomial would be an x plus 1, because 1 is 1 cubed. And then I do that SOPs pattern. The x squared is an x squared. Opposite sign is a minus. Product of 1 and x is a 1x. And then plus, and then the square of 1 is just 1. And then I need to factor x squared minus 4, so x plus 2, x minus 2. So remember on this one, I had fifth power. I'm expecting 5 solutions here. It doesn't mean that they're all real. It doesn't mean any of them aren't repeated, but there should be 5 solutions. So we're going to go through and solve a zero product property now. So 0 equals x plus 1. That one's pretty easy. This middle one, I can tell I am never able to factor it, right? Otherwise, I would keep factoring. And the middle term is odd, so I would prefer to do quadratic formula on that. So I'm going to go over here in some space and do quadratic formula. So let's see, x equals negative b, which would be a positive 1, plus or minus square root of b squared, minus 4 times a times c. They're all pretty much 1s, over 2 times 1. Let's see, 1 plus or minus 1 minus 4 over 2. So that's going to be the square root of a negative 3 over 2. So let's see, this will be a square root of negative 3 will be a square root of 3 times I. So I'm going to have a 1/2 plus or minus square root of 3/2 I. And this is really 2 solutions, right? 1/2 plus the square root of 3 over 2i, and 1/2 minus the square root of 3 over 2i. So really that's 2 solutions. So I already have the x equals negative 1. Where are we at? All right, so we're over here at 0 equals x plus 2. We'll solve that. So negative 2 is equal to x. And the last one, if 0 equals x minus 2, and I add 2 on both sides, then 2 equals x. My last step is to write out all my zeros, which is a pretty big list at this point. Negative 2, negative 1, 2, and then I have that 1/2 plus square root of 3 over 2i, and 1/2 minus square root of 3 over 2i. So just like we were expecting, fifth power, we have 5 solutions. We had some imaginary ones, and there were none repeated on this one. But we did have 5 solutions. So the graph behavior is really something that we don't need at this point. We're going to be looking more at graphs tomorrow. In the near future, I will probably move this to the next day of notes. But when a factor is raised to an odd power, so if the factor is, like, say, x minus k, then the graph is going to cross the x-axis at x equals k. The next one was when a factor, and by a factor, I'm going to say x minus k, is raised to an even power, then the graph bounces at x equals k. So let's look at what that means. So here's my axes. So let's say I have an odd power, and then I'm going to cross. So crossing would look like this. Bouncing is when I go back and I just touch that x-axis and I come back up. So this is a cross. And again, that's when we have a factor raised to an odd power, or just the first power, right? And then bounces when it's being raised to an even power. And again, we'll look more at this with the 5.8 notes. So tomorrow we're actually graphing, not today. Complex conjugates theorem. So we're going to write a long version for this one, and then we're going to shorten it up because they're really similar for the next one. So, and now it's not letting me draw, and I have no idea why. Sometimes it does this. So I'm going to go ahead and read it out loud for now. Complex conjugates theorem is if f is a polynomial. There we go. If f is a polynomial function with real coefficients and a plus bi is an imaginary zero, right? It's a complex number. It has an imaginary part. Then a minus bi is also a zero. So let's think about that really quick. So if we have an a plus bi, in order to cancel all the i's out and end up with real coefficients, we also need to have the conjugate. So we found in our little imaginary numbers unit that when we multiplied something by its conjugate, when we're working with imaginary numbers, all the i's canceled out. We end up with an I squared, but that's something that's real. And so we're kind of using that here. The next one is the irrational theorems. I have no idea how that got there. So I'm just going to delete it, which could be bad, but maybe I can move it. Okay. So the irrational conjugates theorem is talking about irrational numbers that would be like square roots that go on and on forever, pi, stuff like that. So in this case, we're talking about square roots. So this is suppose, actually we'll write it like the last one. If f is a polynomial function with rational coefficients, that means we can write them as fractions. We don't have any irrational stuff that goes on and on forever. And a plus the square root of b is an irrational zero. And you might be guessing where this is going to go. Then a minus the square root of b is also a zero. And my pen quit writing right there. I don't know. For some reason, I cannot write the O on also. There we go. So again, we have conjugates. So we're going to kind of use this on example 3. So on example 3, we're given answers again, and we're going to work backward, and we're going to find our original polynomial function. So it says that we are trying to find the one of least degree. That means don't go through and multiply it by another x. It has rational coefficients, a leading coefficient of 1, and the answers are 2 and negative 2 minus 5i. So if they are rational coefficients, then we must also have the conjugate. Otherwise, we would have imaginary stuff. So we're going to also have negative 2 plus 5i. So remember, we talked about how I could write out all my answers. Right now I have x equals 2, x equals negative 2 minus 5i, and we have x equals negative 2 plus 5i. So then I work to make those factors equal 0 instead. So I would subtract 2 because we're doing 0 product property backwards. This one I'd have to add 2 and add 5i. I should have written these farther apart and spaced them. On this one I'll have to add 2 and subtract 5i. So right now I have an x minus 2 equals 0. I have an x plus 2 plus 5i equals 0. And I have an x plus 2 minus 5i equals 0. So then I'm going to multiply all three of them together. And that's kind of, like I said, 0 product property backwards. So I have an x minus 2. I have an x plus 2 plus 5i. Sorry about that. And I have an x plus 2 minus 5i. And when I multiply all three of them, I'm going to get 0. So I want to look at the structure of this really quick. Both of these have an x plus 2. but one of them is plus the 5i, one of them is minus the 5i. So I want to think about how if I am multiplying out x minus 5 times x plus 5, we know that the middle stuff cancels. We end up with whatever x squared is minus whatever 5 is squared. So I'm going to use that structure here because I have that x plus 2, and then I have the plus or minus 5i. So I'm going to be using that structure to multiply. So my x minus 2 is going to hang out here for now, not doing anything with that. And I'm going to make it a little bit neater so I can read it later. And now I would have whatever x plus 2 is squared minus whatever 5i is squared. So now I'm going to have to go through and work that out. So x plus 2 squared is x squared plus 4x plus 4. We're just expanding that. And this would be a minus 25i squared. We need to remember that I squared equals a negative 1, so I can substitute that. So if I sub a negative 1 in here, negative 25 times the negative 1, I'm going to have an x squared plus 4x plus 4 plus 25. So then we're going to combine the 4 and the 25. This is going to be a long problem. X squared plus 4x plus 29. Okay, now I'm going to go through and multiply by x minus 2. So times x would be an x cubed, and then plus, let's see, 4x squared, and then plus 29x. And then we'll distribute the negative 2. Let's see, so that's a negative 2x squared, a negative 8x, and a negative, let's see, 29 times 2 would be 58. So let's see, x cubed. And then 4x squared minus 2x squared is a plus 2x squared. And then I have a 29x minus 8x, so plus 21x. And then minus 58. And my last step would be to write this. It says write a polynomial function. So instead of equal to 0, I'm going to write f of x equals x cubed plus 2x squared plus 21x minus 58. And these are our 5-7 notes. Make sure you let your teacher know if you have questions.